Super. Well, welcome everybody. Again, my name is Sally Allen and I'm with the Livermore Lab Foundation. I'm so happy to have you here with us today for Ask a Scientist, Staying Entertained with Physics. Today our featured speaker is Dr. Leah Ellison with Lawrence Livermore National Laboratory. And the foundation is thrilled to have this collaboration with the lab and with the Livermore Valley Joint Unified School District to bring you access to these amazing scientists right in our own backyard. Before we get underway, I just want to quickly introduce a couple of my colleagues with me today. Susan Houghton, who is our behind the scenes moderator. She's helping get folks on board today and will also be helping manage our questions in real time as they come in. Thank you to those of you who already submitted questions in advance. It's been terrific to get us excited for today. Also with us from the school district, we have our Assistant Superintendent, Mike Biondi, as well as Kevin Greer, who's our Director of Curriculum and Instruction at the district. They've both been really instrumental in helping us spread the word about this series, so thank you both. And lastly, from the lab, we have Nadine Horner, who's part of the community relations team at the lab, at Lawrence Livermore Lab. And last but not least, Dr. Leah Ellison. Is it okay to call you Lee today?
That's great.
Okay. Thanks so much for being here. So let's go ahead and get started. Just quickly, as you likely know, this is the second in a four-part series that the foundation is hosting for Ask the Scientist. We had our first one earlier this week on planetary defense, which was well received, and we have two more coming up next week. They'll be on Tuesday and Thursday at 1 o'clock. All of the information that you see on this slide right now is also on our website, which we will share with you a little bit later. And we encourage everybody, actually the website is up there on the slide too. Please go ahead and sign up. We'd love to have you participate in all the rest of these. We're really excited and hope to continue them into the fall if possible. Next, just a couple of quick housekeeping items. So as you joined today's meeting, we have everybody on mute just for the sake of being able to manage the sound and the recording. But if you, at any time during today's talk, if you have a question or a comment, please use the chat feature. I think hopefully most of you are familiar with the Zoom interface at this point with all of the distance learning going on. So go ahead and send a question via chat, and Susan will be in touch with you. If you also are feel comfortable, we'd love to have you turn on your video, and we can do that on our end, and you could ask your question directly of Lee. So we have some questions that we're going to start with that we got in advance, and then we'll open it up to a Q&A period. And last, as I mentioned, we are recording today's talk, so you'll be getting a link to that probably by the end of next week. So without further ado, I'd like to introduce Leah Ellison. I'll give you a little bit of background on him, and then I'll hand it over. You may already be familiar with him, as this video that you watched most recently for this talk today was part of a series that he has produced on YouTube. He's a burgeoning sensation, learning with Leland. So this is just a screenshot to give you a sense of what else he's been doing on there. He originally grew up in Denver, but he lives now in Livermore, and he's been at the lab for about 4 years. And very busy as a computational physicist. I personally am interested in hearing more about what that actually is and what you do on a daily basis in your job. A couple of quick fun facts just to get to know him better. He is a PC gamer. He's a Diamond League StarCraft 2 player and a Platinum rank Apex Legend player, which I'm sure is very impressive to the right people in this audience. He also played bass for a singer-songwriter in college and had one of his songs performed on the TV show One Tree Hill. So he is a man of many talents, and we are thrilled to have you today, a real expert in your field, Lee. So thank you for your time. And I'm just going to kick it off by asking if you can share a little bit about yourself, and especially about the video that all of the students that are here today hopefully watched in advance, and kind of what went into putting that together.
Thanks so much, Sally. I really appreciate the introduction. And thank you all so much for attending. I'm really flattered to have the Livermore Foundation and the Livermore Schools invite me to come and speak with all of you. It's a real honor. So I have to admit, I was a little nervous to share my fun facts about myself. I don't know if any of the students out there have come to Livermore for our Fun with Science events, but we have these events where we bring students in and we do scientific demonstrations, and they're a lot of fun. And I've been presenting with Fun with Science for 2 or 3 years now. And at one of the very largest Fun with Science events that we have, we fill one of these large auditoriums with many students from all sorts of school districts. There's 300 kids in the auditorium. And as I was leading up to tell them about how great it is to come to Livermore, where we have the biggest supercomputers in the world, like I'm about to tell you, I told them that I play Apex Legends. And all at once, unanimously, the 300 kids in the audience booed me. So I'm under the impression that there are a lot of Fortnite fans out there, maybe not so many Apex Legends fans out there. So I hope that fact about me hasn't deterred anyone from sticking around here. Fans of all games are welcome to listen. So thanks for coming in. So before talking about the demonstrations and the video, and you guys asked some really great questions that I look forward to answering, I actually didn't spend a lot of time in the video that I made talking about the work that I do. So I wanted to kick things off with a little bit more detail about what makes my job so much fun at Livermore. I really am very passionate about scientific outreach and doing basic physics that everyone can do at home. But the thing that I'm most passionate about that gets me out of bed every day is the really fun job that I get to do. So I'm so excited to have this dedicated platform to share with you those details of my job. So maybe we can go to the first slide. Maybe it's showing up. I'm not sure how that goes. But one of the things that makes working at Lawrence Livermore so awesome is that we have some of the biggest toys in the world. Now, by toys, of course, I mean precise scientific instruments. The point of a toy is just to entertain someone, and these devices are not for entertainment. We don't play Apex Legends on the supercomputer here. They're for doing scientific research. We get technical results that society and the government are interested in getting, but that doesn't mean it's not fun to work with these tools. So I hope to give you a sense of what those tools are and kind of a little glimpse of a day-to-day inside the life of a computational physicist. So as we've already discussed, let's keep on the first slide. When I come home in the evenings, I work very hard at my PC gaming and climbing those ladders, get all the ranks up. Many of you at home might also play some games. Maybe you have an Xbox or a PC. And basically any modern electronics for playing video games is going to have a graphics card in it, right? You might have an NVIDIA one or an AMD one, but it's a piece of computing hardware that really specializes in performing the mathematical operations to make those images on your screen. So when I go to work, I also use graphics cards. But I don't just use one or maybe two really high-end computers, have two graphics cards working together in them. I have never owned one of those. But at lab, we have a new supercomputer. It's number one in the world, and it works off of graphics cards. In fact, we have 17,000 NVIDIA graphics cards. These are really, really high-end ones. You can't buy them for your home computer. Each one is extremely powerful. And we've networked 17,000 of them together to communicate with each other all at once so that we can perform the most precise scientific calculations that have ever been done. So it's one of many impressive computers at Livermore. We have 6 on the top 100 supercomputer list. We're getting new ones all the time. They barely get one on the ground before they start procuring the next bigger and better one. But right now we're really excited about this one called Sierra. You can see the computer in the top right picture. There's some nice blue lighting, and basically those cabinets there are filled with little server racks. They have glowing lights on them, and they have those NVIDIA graphics cards inside of them, and there's all sorts of wires behind them to make sure they talk to each other. A ton of people work really hard to make sure it can work together. In fact, it draws so much power, it's over 10 megawatts of power to run those computers and keep them cooled. That's basically enough to run a small city. In fact, Livermore has to call the power company if we're going to turn a computer off and suddenly use much less power, or ramp up a really expensive calculation. It's big enough that the power companies need to know about it so they can adjust and make sure that us residents at home aren't getting our lights flickering when changes happen to the supercomputer. So hopefully that gives you a big sense of scale of really what impressive machines these are. So what do we use them for? At the end of the day, what we do with the supercomputers isn't all that different than what Pixar or Disney does when they make computer animated movies. Probably a lot of you have seen some Toy Stories or Finding Nemo or one of these fabulous movies. For those, they have software developers who develop tools that model how light bounces around, how it goes through water, maybe bounces off the skin of a fish, maybe goes through some glass or something. They're solving mathematical equations in order to have that move around. They have users who will do the art of what is the specific shape of my Nemo fish or whatever the character that you're looking at is. And then they use some large computers, not as big as the ones we have at Livermore, but some large computers to render some images at the end of the day that are stitched together to make the movie that you watched, right? So that's what we do on these big computers. We solve equations for how light moves around, how it interacts with matter. And at the end, what comes out is a very detailed movie. Now, unlike a Pixar animated film where the point of the movie is to be artistically pleasing and tell a really nice story, the point of our movies is not to be interesting to look at, it's to be the most accurate predictions of some specific experiment that we know how to get. These computers really embody a history of knowledge. We write down the physical laws that we think are important for governing these systems. And when we write those down, they're too hard to solve with pencil and paper. We have to use these large supercomputers to solve those equations. But what comes out at the end is kind of a movie of some physical process. So before talking more about what those movies kind of look like, I want to talk about what we're actually modeling on these big supercomputers, and that'll take me to the second slide here. So we use this and other supercomputers to study a lot of different things. One of the big ones that I care about is experiments at the National Ignition Facility. So Livermore is not just home to the second largest computer in the world, it's also home to the #1 largest, most energetic laser facility. It's extremely impressive. You might have seen it if you drive down Greenville Road. On the top left, there's kind of a cutaway of the building. It's a large yellow tan kind of building, might look like just a lot of offices if you're looking at it from the outside, but in this artistic rendering, we can see it opened up and we can take a look at all the stuff inside of it. This building is huge. It's longer than a football field. It's filled with all of the instruments needed to drive this largest laser facility in the world. So in the back of the building, far away from the cutaway that we have here, there's a bunch of capacitors. They're basically like batteries, but they can discharge very quickly. And that's what we charge up to power this largest laser in the world. And then when they go to fire it, those capacitors will dump their energy. There's some long white tubes that you can kind of see on the left and the right of that image. And the laser light bounces back and forth through that. And it charges up, builds more and more energy through every pass. And eventually it all gets piped down. We have 192 laser beams. It gets piped down into this giant metal sphere. You can see that my orange arrow is pointing to it. That's at one end of this building, and that's called the vacuum chamber. So the vacuum chamber itself is huge. You can see on the bottom left picture a photo of the vacuum chamber being installed, and it's being lifted by a giant crane. The big orange thing behind it is a big crane. You can see some tiny little people standing in front of it. They're normal sized people, I assure you, but they appear tiny relative to this giant vacuum chamber. So the 192 laser beams come piping in through all those little windows in the vacuum chamber, and they shine inside of it, rotating around kind of counterclockwise here. On the bottom right, we have a person in some protective gear. They're standing now inside that big metal chamber, and they're setting up one of the targets that we will shoot with the lasers. So these lasers have gone through this football field length facility, charging up all this energy. They shine into this vacuum chamber, and ultimately they end up inside this tiny little gold cylinder on the end of this big arm. And there's kind of tweezers there you can see. It's very small. On the left end of those tweezers, there's a little gold cylinder. It's about ½ inch long, and all 192 laser beams shine on the inside of that. So this happens in the time scale of just a few billionths of a second. It's really a marvel of modern engineering that we can point 192 laser beams to focus them extremely precisely, tiny, tiny, tiny fractions of an inch. We shine them inside of this little gold cylinder, ½ inch wide, and they dump all of their energy in a few billionths of a second. So you can imagine when we shine all that energy on this gold cylinder, it starts to heat up a lot. And that gives off X-rays. They bathe this tiny sphere. You can see in the top right artist's rendering of this gold cylinder that there's like a white sphere there. It's gonna get really hot, really fast, and it's gonna get squished down. So our experiments at the National Ignition Facility are ultimately about taking that sphere that you see right there and driving it down to really, really small size, but then extremely high density and extremely high temperatures. So when we squeeze these millimeter-sized spheres, they're usually like plastic on the outside, and they'll have some hydrogen inside of them. Those plastic spheres will shrink by a factor of 20 or 30 in radius. So to give you a sense of scale, if you take a bowling ball and you squeeze it from all directions and shrink it down to the size of a marble, that's squeezing it by a factor of 10. So at the National Ignition Facility, we go a factor of 20 or 30. It's really extreme conditions of materials to take something that starts off solid density and shrink it that much, as well as to heat it up so much. When it absorbs all of these X-rays, it heats up hotter than the surface of the sun, but so dense that in nature, we only see these densities at, say, the interiors of planets like Jupiter or in stellar objects. So that's really what this long story about what are we doing with this giant facility is about, is this allows us to access regimes of physics that we aren't able to in normal circumstances. These are extremely hot conditions, extremely dense conditions, and having the ability to do this in a laboratory on a very safe, small scale, it's a lot of energy, but at the end of the day, you can see our target is just this tiny, tiny little thing, and it allows us to answer a lot of really important scientific questions. We can learn about how the materials at the centers of planets like Jupiter behave when they're under such extreme conditions. We can learn about how light moves around in the sun as it's making its way from the core outside and coming to our planet. We can learn about the material properties that are really hard to understand without an end of the day measurement to tell you what's happening. Another important aspect is we can learn about how nuclear weapons perform without having to conduct a large, potentially dangerous experiment in a desert somewhere. This is a safe way to answer the questions we need for a national security perspective, but without having any of the bad side effects of actually testing weapons. So it's really a national treasure that we have this facility in our backyard. So I've explained to you that a lot goes into these experiments at the National Ignition Facility. We dump all this laser energy, goes through this massive process and squeezes this tiny little sphere. They only do that about once a day. You can imagine it takes a lot of people working very hard, working together to make this happen. And once a day is very fast for being able to do these experiments, but we want to be extremely careful that that time is well spent. So for every one time they fire the National Ignition Facility, they run hundreds of computer simulations to design the experiment and make sure that we're going to be able to get the measurements out that we're interested in. So that's where my job comes in as someone who writes software that is run on these massive supercomputers, is making sure that people who are designing these experiments at the National Ignition Facility are going to get the results that they want. So I'd actually like to go back to, in the first slide that I had, I linked to a YouTube video. And that YouTube video is made by a code that I work on and was done as one of the very first proof of principle that we could run calculations on this giant supercomputer. So it's moving along, there's kind of some text at the beginning, but what you're gonna see is a Sierra supercomputer rendering of something that mimics a lot of the important processes happening at the National Ignition Facility. So this talks about some instabilities. Inertial confinement fusion is the type of experiments we run at the National Ignition Facility. Can we pause it right here? Perfect, okay. So what you see, we have this red disc on the outside. That's like the plastic that sits at the center of the National Ignition Facility. This is a tiny little disc of plastic, and it's gonna get flooded with energy from around the outside. Now, we really want to squeeze this thing as uniformly, smoothly as possible, but even with 192 laser beams and this gold cylinder that helps to smooth things out, there's always going to be some little differences. And the simulation is going to show you how those differences grow in time. And we're going to see the plastic red on the outside mixing with some blue, like hydrogen, on the inside as it's getting squeezed. So, okay, let's go ahead and play that forward. Okay, so you can see we're squeezing this in. We got these little fingers that come in as this guy is getting squished. Overall, it's also shrinking a little bit. And you can see some mixing. The white areas is where the red and the blue are mixing together. Okay, and now you can see there are certain parts that haven't moved as much. They're on the outside, they're not being pushed as hard, whereas there are other bits that are on the inside, they've been squeezed more. And now we get this movie of what happens, and we can look late in time at very specific details of how this mixing is happening. So at an experiment that happens on a few billionths of a second, it's really hard to know what specific details there are. The beauty of computer simulations is that we can look in, inspect the tiny little nuanced aspects of our approximation of what's happening to the experiment. So it's really this interplay of having the simulations where you can look at everything in detail, but it's approximate, it's not nature's bottom line answer of what happens, and the experiment that gives us the real answer that nature is doing, but is really difficult to see what each individual detail is going on. So, so that calculation ran on the Sierra supercomputer and was a big success for us, showing that we could get our physics codes to work on such different hardware that takes 17,000 GPUs working together. So hopefully that gives you a bit of an idea of what a computational physicist does. I spend a lot of time developing computer software. As much the product at kind of the end of all this is these movies that represent experiments that happen at the National Ignition Facility. And certainly the product of that is having a better understanding of what happens to materials when they're under extreme conditions, high densities and high temperatures. But I don't spend most of my time watching movies like the one we just looked at. A lot of it is kind of under the hood, so to speak, working on the engine. I will open up piece of text that has computer code in it. Some of you might have started to learn Python or C or C++. These are all really great skills. I use those skills every day and develop computer code. And I spend a lot of time digging into the details of, hey, how do we solve this particular physics equation better? And hey, this measurement we got on the experiment doesn't match the prediction that the code gave ahead of time. What sort of things might we be missing, and what can we put into the codes to make them more accurate representations of nature? So if you have questions about what a computational physicist does and those aspects of my job, I'd be happy to field those. But first, I think we have a couple questions, maybe a bit about that and also about the demonstrations that happened in the YouTube video.
Yes, Lee, thank you so much. I learned so much in the last 10 minutes. That was amazing. I really appreciate it. So, and actually that's a great segue into one of the first questions we had from a student named Ava. She asked, do you have to be good at a specific thing in order to be a scientist?
Thanks for the question, Ava. In short, I would say no. I would say no from two perspectives. One is that I think to be a good scientist, it takes a lot of different skills. Certainly, being able to learn mathematics and learn physics is an important cornerstone to the job. But what I've seen as I've gone through my scientific career, you know, when I was in middle school and high school, it was about, hey, can you solve this particular math problem? We're going to teach you about algebra and we're going to have you solve this question. And it's a very yes or no, you got it right or you didn't, maybe you get some partial credit. When you get to a research level position, there's an important core technical skill set of the mathematics that is there, but it's also really important that you can communicate your ideas. Scientists are really measured by the publications they put out, and if other scientists read their publications, and if they were able to convey the importance of the results they were doing. So communication is a really important skill, as well as being able to work well on teams. I mean, in the two slides, you heard about, we have huge computers and it takes all sorts of skill sets to just make those computers work. And then we have huge experiments and it takes all sorts of different skill sets to make those experiments work. And every day I go to work, I don't have all the answers. Even after all the schooling that I've done, I have to talk with a lot of people who know about different subtopics of physics and math and computer science and learn from them and express my questions to them. And so it's really important to have teamwork. So I think there's a lot of skills that you need to have. Certainly some of them are essential, but I worry that some people think, you know, I took a math class and it was really hard. Maybe I'm not cut out for the sciences. I hope that if you find these ideas and questions really interesting, that you'll stick with it, because at the end of the day, the other really, really, really important piece, you can be as smart as you want, but it takes a lot of hard work. And I would say the most essential aspect to being a successful scientist is to be curious and willing to work hard. I think what I share in common with my peers who have gotten to this point in scientific research is we get bitten by the intrigue of a particular puzzle and our brains keep chewing on it. I'll have something I'm trying to figure out at work and I go home and it's not unpleasant. It's not like I'm working hard, having to keep working. I'm having fun attacking this puzzle from different directions and trying to figure out how it makes sense and how to piece it together. And it's sort of that insatiable curiosity that I think is the most important aspect of being a research scientist.
Great. Thank you so much for that. And thank you, Ava, for the question. I think I'll shift gears a little bit and ask you a couple questions that came in about your video that everybody saw.
Great.
If that's okay. You did two experiments there. One was about the eggs and how to detect whether one was hard-boiled without actually cracking it open. And the other one had to do with supercooling water and the crystallization process, which was very cool. So there were a couple questions related to the egg experiment first. One was, what's actually happening to the yolk inside the egg during the hard boiling process? And another related was, why did they spin in a circle? Or, you know, what affected the way that they spun on the counter?
Yeah, both great questions. The first one is really interesting, and I had to think about it and do some research to make sure I had a right answer about that. It was not at all obvious to me what is happening on a microscopic level for the yolk, which starts off all runny and liquidy at first, and then you cook it and it congeals into this hard, firm, kind of solid thing, right? And I learned some things myself in researching this. So I think it was the Exploratorium had a really nice discussion of egg science online. So I need to credit them with my answer here. So the picture they gave that I think makes some good sense is that eggs are basically made up of proteins, right? These proteins are kind of these long molecules or these long chains of amino acids, maybe like a big piece of yarn. But when you have an egg fresh out of the fridge and it's all liquidy and runny, those proteins are all wound up into these tiny little balls. It's like you have balls of yarn that are distinct, separate ones. And when they're all wound up in those little balls, then they can slip slide past each other like a bunch of marbles in a jar or something. And that's what keeps them liquid. But as you heat it up, heat is just the motion of atoms. If I'm in a hot room, the atoms in the air are moving around faster than in a cold room. They're moving slower. So as you heat things up, these balls of yarn start to kind of untangle, and they can start to lock together one another. So if you unrolled a dozen balls of yarn in a living room and unleashed a bunch of cats to go bat them around and they're all unraveling, you can imagine that those balls of yarn are likely to tangle up and start to kind of weave together. It's probably a big, messy, knotted weave, but you can imagine if you pull on one, it's not going to just come out by itself and slip slide past the others. They all get knotted and they bind together. And that's basically what happens when you hard boil an egg. You're adding heat, those proteins kind of unfold from their little yarn balls and they start linking each other together, and you get this firm structure of this kind of giant proteins locking arms together rather than that liquid where all the proteins are slipping past each other. So great question there. Thanks for making me go learn a bit more about how eggs are working every time I cook them. I will think about that every time now forward. A different question, also great, about noticing some aspects of the spinning of the egg. So you might imagine that we could spin the egg and it would sit perfectly still and just rotate about the point it was sat on. But that's not really what we saw on the counter, right? It was kind of processing around in a circle as it was spinning and spiraling. And I think that's kind of what this question is about. So I don't know that I have a really concise, nice kind of mental picture to explain that additional processing motion. But the things that I think about are, as I'm spinning it, I'm applying a little bit of force to it, and it's very hard to have kind of my two fingers that are spinning it give exactly the same amount of force. And if there's any imbalance, it's going to start moving in that direction. But it might also be tilting, kind of like a top. And so as it's tilting, gravity is going to be pulling it down one way, and that sort of tilting motion with gravity pulling it towards the center as it's tilted is probably what makes it move in that larger circle pattern, kind of superimposed on the tiny little rotations that it's doing. So I hope that makes sense a little bit. If you're interested in that question, that's something that college level physics digs into a lot. They'll teach you some equations you can write down, and they have some very bizarre tops where professor will spin the top and it moves around kind of like we saw, and then it'll flip upside down and suddenly be spinning on its tip and might flip back. Some very, very counterintuitive, surprising things can happen. And digging into the math and trying to understand what governs those surprising behaviors can be a lot of fun. So that's a great physics question you asked.
Yeah, that's really what physics is all about, right? Discovering why things are happening in the world that you can see and sometimes not see. So
Exactly.
Thank you.
Exactly.
We had a question about the water experiment from Amara. She wanted to understand better why the pure water didn't freeze until you hit it.
Right. Great question, Amara. It's awfully surprising, right? I love that demonstration because it again challenges our intuition about what happens to things. So it's surprising because we are told water freezes at 32 degrees Fahrenheit, right? And now we find that in certain circumstances, that's not quite true. I had two water bottles, and one of them froze when it got below 32 degrees Fahrenheit, and the other one didn't. So that process of taking water below its normal cooling point is called supercooling. I use that phrase in the video, but just a phrase doesn't tell you how to understand what's happening, right? It's just a name for it. So it turns out that you can actually, if a water is very, very, very pure, you can supercool it all the way down to negative 55 degrees Fahrenheit before it will spontaneously form that crystallization process. So to kind of understand why that's happening or why the purity of the water has an impact on that, say, we need to have a good mental picture of what's happening when the water is freezing. So this comes back to kind of like our proteins yarn ball analogy that we had a minute ago. Water is these little H2O molecules, right? Some hydrogen and some oxygen, and they're moving around. And normally in the liquid state, these are close together, but they're kind of slip sliding past each other. In the solid phase, the little hydrogens on the ends, these, my fists are the oxygens and my fingers hanging out here are my two H's. When you go to solid phase, the hydrogens kind of start to lock together and you can get these little chains of molecules that aren't moving independently, slip sliding past each other all the time. They're locked into this chain link, we call it a crystal lattice. So ice happens when water is locked into this crystal lattice. The molecules kind of lock arms and get a rigid orientation relative to one another rather than slip sliding past each other. And it turns out that when that happens, it's really helpful for that chain linking to take place to have a good starting point where they're encouraged to start linking hands and locking together rather than just slip slide past each other. And so a technical phrase for that is a nucleation site. People talk about this with moisture in the atmosphere and making clouds. You might have a little speck of dust that is a nucleation site and the water will condense onto it. And now you can kind of see this cloud. In my tap water bottle, there's all sorts of stuff that's not H2O. My tap water wasn't perfectly pure. There's maybe a little bit of mineral content from my pipes or something like that. And it's actually those impurities that form these nucleation sites and this starting point for this lattice to grow off of. And so with normal water, there's lots of these nucleation sites. Is when it hits 32 degrees, it can start linking hands like we described and kind of grows the crystals out from there. But when we have a really pure water, we've taken away all those nucleation sites. And so it sort of takes a lot longer in terms of temperature and maybe time in order for the water to be able to link hands and make that rigid lattice solid phase thing. So that's kind of an intuitive mental picture of what's happening and what I have in mind there. There's a lot of pieces to this that I don't really understand. It's not obvious to me. I haven't done a calculation that says, I can see why negative 55 degrees is really special for even the purest of water. I don't know. I'm sure people know, and we could do an experiment to decide this. If I left my water bottle at 10 degrees Fahrenheit, would it have eventually frozen? Is it just a lot slower? This supercooled mechanism definitely has some subtle, interesting physics going on, and there's a lot to learn there.
Very cool. Thank you so much. I want to briefly just encourage folks to turn on your video. If you are interested in asking Leah a question yourself, I'm sure people have been sending questions to Susan, but we're happy to see faces too. So please feel free to do that. One last question, and then I'll turn it over to Susan. I think it was Ava again. She wanted to know, how do you learn these tricks that you had in the video? I'm sure other students would like to know, where can they go to if they want to do some of these experiments at home?
Oh, great question. So the supercooling one, I don't remember where I first heard about that. I do remember watching some YouTube videos, and I certainly did some Googling to learn how to do it myself. You saw in the video, I tried to do it with an ice bath first, and I think that was a really difficult way to go. It didn't work for me at all. I think maybe someone was suggesting that if you want to do it in your classroom where you don't have a freezer, that could be a good way to go. But the freezer was much easier. So I don't remember where I first heard about that. The egg demonstration, I actually have a very clear memory of when that happened. So when I went to college and at the University of Colorado in Boulder, we had a once a semester outing with the physics professors, and I forget what the criteria was, the physics students on the honor roll or something, but it was students who had done well, and they would take us to dinner and they'd buy us dinner, and to keep the conversation going and keep us having fun, they would have some physics puzzles for us to talk to each other and try to sort out. And one that I really remember was they gave us 2 eggs, and we're sitting at a dining table, a nice restaurant, and waiting for the food to come, and they say, okay, figure out which one of these is hard-boiled, and you can't crack it open because then no one else can try this. And it took us a lot of time of playing with them and looking at their properties to try and see what might be different. So I remember very clearly that kind of puzzle coming up. Maybe one I'll give you guys, and you can challenge your teachers and they'll be frustrated at me for not giving you the answer. Another one from that dinner that I remember was just a riddle. You have a ruler, 1 foot long, and you have 100 ants. And the ants move at 1 foot per second. These are very fast ants. Now, these ants are sprinkled randomly on the ruler. Some of them are going left, some of them are going right. They bounce off of each other in a momentum conserving way, of course, like good physics ants do. And the question is, how long until you know for sure that all 100 ants have run off the edge of the ruler? So I will just leave that as a riddle, and maybe you guys can think about that with your teachers.
I know, I don't think I have an answer right away.
It's subtle.
Thanks so much. Great. Well, I think I'm going to check in with Susan. How are we with other additional questions, Susan?
We have 2 questions, Sally. The first one, a student wants to know what happens at the center of, they're saying what happens at the center of Jupiter is cool, but is there any practical use for that in everyday life?
Great question. So yes, I think, and there can be several steps between, I would say that's kind of a basic science question. And it's often a question that comes up of like, well, what's the usefulness of basic science? But I think when you realize how many things are interacting, then the individual pieces stop seeming very isolated and perhaps irrelevant to other things that we might care more about. So I would say understanding how materials behave at extreme conditions helps us understand things here on Earth. We're always coming up with new ways to put materials in extreme circumstances. I mean, you think about, this is kind of a stretch, but things like quantum computers. Those aren't related to these really high densities and temperatures that we discussed, but they grow out of our understanding of some experiments that many years ago might have taken large experimental facilities or considered these really extreme, hey, this is really cold and it just happens a few atoms at a time. How is that relevant to things we care about these days? As you build up these building blocks of basic science is where you get to the applied science, and there can often be unexpected consequences of how that works. I would say in the specific case of Jupiter, understanding how these materials behave gives us a lot of understanding in our astrophysical measurements. We are looking at how light is moving around in space and how it comes off of other planets. Maybe if we can understand the dynamics of Jupiter better, we can go learn things about, we get a little bit of light from a planet very far away and we want to know if it's Earth-like and inhabitable. And knowing some basic things about how the matter behaves inside Jupiter can help us answer those sorts of questions. So I'd say, one, it helps us as we take materials to extreme conditions here on Earth. And two, it helps us understand astrophysical sciences better. And finally, there might be things down the road that we can't think of right now, but having that good scientific understanding will enable it to happen.
Okay. We have another question that's come in, Sally and Leland, and this is about the simulation that you showed in the supercomputer. They want to know, how much does it cost to fire up the supercomputer like one time to do that simulation, and how much energy does it take?
Ah, great question. So the supercomputer is on all the time. Basically, once we put it on the floor and we turn it on, initially it might be kind of fire it up to run it. But after that, we have users who are submitting, we call them jobs. They're kind of submitting calculations to the computer all the time. And in fact, we always have a big list of jobs that we'd love to get through, but there's a system that decides who gets the next turn. And a lot of times you're not using the whole machine at once. Certainly we do use it for some really big calculations. That's kind of the point of having all these graphics cards able to talk to each other, is really, really big ones. But we also use maybe only 100 at a time for smaller calculations. So it's basically running constantly, and it takes about 10 megawatts of power to run that. So I don't know what the lab's electricity bill is for 1 year of running the supercomputers. Maybe one of the people on the phone has a better, more specific answer for that.
$1 million per megawatt.
$1 million per megawatt?
Yep.
Wow, for a year.
Yeah, so that's $10 million just for the power.
Wow, wow. Thanks. So we have a treat that Donna Crawford was in the computation directorate for a long time, leading it, and was involved in getting those computers on site, so she knows well. So about $10 million a year just in the power to run that computer. I think the movie you guys saw is only like a couple of days worth of that, and that's in early time, and we're still smoothing things out. So that might give you a sense.
Great. Susan, are we good?
I think we're good. Yes, we're ready to move on.
Okay. I have one last question for Lee is, are you planning any additional videos coming up?
Any videos? I don't have any specific plans. They're a lot of fun to make, but also a lot of work. If you guys have experiments or questions that you think might be fun videos, I would love to hear ideas. A lot of the hard parts coming up with what the content should be. So please send forward your requests, but I don't have anything on the calendar right now.
Okay, great, thank you. And if, yeah, if folks have ideas, you can always send them to the foundation. It's info@livermorelabfoundation.org. Lee, thank you so much for joining us today and sharing more about what you do at Lawrence Livermore National Lab and your job. It's really exciting. And for those of you out there, just a reminder, Lee is one of thousands of scientists right here in our own backyard, doing incredible, interesting experiments and practicing science every day. And so it's a real treat to get to meet you today and learn more about that. And if people are interested, I would encourage you to check out the Foundation's website. We are at livermorelabfoundation.org. We were created about 4 years ago specifically to help inspire the next generation of scientists and engineers, both at the lab and in the world. And so it's a great resource, and we are here to try to build a bridge to the community and provide more opportunities for students like you to learn about what goes on at the lab and what these scientists do and how you might become one someday if you're interested. We also have a newsletter that you can sign up for on our website, so I would encourage you to do that. So I think we're at almost about time today. Thank you everybody for joining us, and it was great to have you. And remember, next week we will have 2 more of our Ask a Scientist events, Tuesday and Thursday at 1 o'clock. So we hope to see you there. And with that, I think we are adjourned. Have a great day, everybody. Thank you.
Thank you
Lee.
so much, guys. This is a real treat.
Bye-bye.